Is the emptiness of space truly empty? What we perceive as a void is actually a seething sea of quantum activity, a cosmic dance of energy where particles flicker in and out of existence in the blink of an eye. These are quantum fluctuations, the universe's own background static. They are tiny, unpredictable changes in energy happening everywhere all the time. By the end of this journey, you will have explored 30 incredible theories that reveal how this nervous energy might hold the keys to everything from the Big Bang to parallel worlds. We will investigate how these tiny jitters could have built the entire cosmic web and whether they are writing the final fate of our universe. What single mystery of the cosmos most captivates your imagination? Our very first theory confronts one of the most baffling problems in all of modern physics. It is known as the Vacuum Catastrophe, and it begins with a simple, profound question. What is the energy of nothing? According to our best theories of the quantum world, the vacuum of space is not a true void. It is a vibrant sea of zero-point energy, a background hum of activity caused by quantum fields constantly fluctuating. These fields are not made of particles but are more fundamental, the underlying fabric from which particles like electrons and quarks briefly emerge. The mathematics of quantum field theory allows us to calculate the energy this seething vacuum should contain. The answer it gives is staggering, a number so immense it defies human comprehension. This vacuum energy should act as a repulsive force, a cosmological constant driving the universe to expand at a ferocious, uncontrollable rate. In such a universe, galaxies would never have formed. Stars would never have ignited. The cosmos would be a thin, cold, and utterly lifeless haze torn apart by its own empty space. Yet that is not our reality. Our universe is expanding, yes, but at a relatively gentle pace. Observations show the actual energy density of the vacuum is at least 120 orders of magnitude smaller than the theory predicts. To grasp that number, imagine the difference in size between a single proton and the entire observable universe. That is the scale of our error. This is the vacuum catastrophe. It is not just a small miscalculation, it is a screaming contradiction at the heart of physics. It tells us that something is profoundly wrong with our understanding. Either our theory of quantum fluctuations is incomplete, or our theory of gravity is flawed, or both. This colossal mismatch forces us to question everything we think we know about the energy of empty space and the very forces that shape cosmic destiny. How can nothing be so full of potential, yet so strangely quiet? The answer remains one of science's greatest secrets. This staggering error in our understanding of nothingness leads us directly to a moment of creation. The vacuum catastrophe hints that our theories are incomplete, but one idea provides a spectacular triumph for quantum fluctuations. It is the theory of cosmic inflation, a concept that solves multiple cosmic puzzles at once. Picture the universe in the first fraction of a second after the Big Bang. It was unimaginably hot and dense, but then something extraordinary happened. A strange field, known as the inflaton field, is thought to have taken over. This field possessed a tremendous amount of potential energy, which acted like a form of anti-gravity, causing the fabric of space itself to expand at an exponential rate. In less than a blink of an eye, a subatomic speck of reality was stretched to a size larger than our entire observable universe. But what does this have to do with quantum jitters? Everything. Even during this hyper-fast expansion, the inflaton field was not perfectly smooth. It was subject to the same quantum fluctuations that pervade all fields. Tiny, random variations in its energy value flickered in and out of existence. As space inflated at a dizzying speed, these microscopic ripples did not get smoothed away. Instead, they were stretched and frozen into the very fabric of the cosmos, magnified from the quantum realm to astronomical proportions. These amplified quantum ripples became slight differences in density, tiny hills and valleys in the distribution of matter and energy. They were the primordial seeds for all the structure we see today. The evidence for this is etched across the sky in the form of the cosmic microwave background, the ancient afterglow of the Big Bang. This fossil light shows minute temperature variations, patterns of hot and cold spots that match the predictions of inflation perfectly. These spots are the direct imprint of those original quantum fluctuations. Over billions of years, gravity got to work on these seeds. The slightly denser regions, the hills in the cosmic landscape, pulled in more and more matter through their gravitational attraction. They grew into vast clouds of gas which collapsed to form the first stars and galaxies. These galaxies then clustered into the immense cosmic web we observe today, a tapestry of filaments and voids spanning the entire universe. So the grand tapestry of the cosmos, with its billions of galaxies and trillions of stars, finds its ultimate origin in the tiniest of quantum tremors. The very galaxy we call home, the sun that warms our world, and the planet that gave us life, all trace their existence back to a microscopic quiver in an energy field during the universe's first fleeting moments. It raises a humbling thought. Are we and everything we see simply the amplified echo of a quantum whisper? Yet if those quantum seeds built our entire cosmic landscape, what does that say about the nature of reality itself? A third theory offers an answer so radical it challenges our most basic perceptions. This is the holographic principle, the idea that our three-dimensional universe, with all its depth and volume, might be nothing more than a projection from a two-dimensional surface. Think of the hologram on a credit card. It appears to have depth and solidity, a three-dimensional image you could almost reach into. But all that information, every detail of that seemingly solid object, is actually encoded on a flat, two-dimensional film. The holographic principle suggests our universe operates in a similar way. All the information that makes up you, me, the planets, and the stars, every quantum fluctuation and event we experience in three dimensions, could be entirely encoded on a distant, two-dimensional boundary that surrounds us. In this framework, the quantum fluctuations we have been discussing are not the primary reality. They are instead a projected consequence of information being processed on that ultimate cosmic screen. The seething, flickering energy of the vacuum and the primordial seeds for galaxies are all just a three-dimensional translation of data written on a two-dimensional surface. This bizarre idea did not come from nowhere. It emerged from a deep conflict in physics known as the black hole information paradox. Black holes, according to our current understanding, have a property called an event horizon, a point of no return from which not even light can escape. If you throw an object, say a book containing vast amounts of information, into a black hole, that information seems to be lost forever when the black hole eventually evaporates. This violates a fundamental law of quantum mechanics, which states that information can never be truly destroyed. The holographic principle resolves this paradox beautifully. It proposes that all the information about what falls into a black hole is not lost inside its mysterious interior. Instead, it is perfectly preserved, encoded as quantum fluctuations on the black hole's two-dimensional event horizon, its outer boundary. The three-dimensional space within the black hole is just a projection of that data. This means the fundamental building blocks of reality might not be particles or fields in space, but bits of information like the ones and zeros in a computer written on the cosmic boundary. The quantum fluctuations we observe would then be the pixel-level noise of this grand cosmic projection. If this is true, the very fabric of space-time, with all its wrinkles and ripples, might not be fundamental. It could be an emergent property, a holographic illusion generated by a vast, complex computation happening at the edges of our perception. This leads to a staggering implication. The entire cosmic history we explored, from the first inflationary jitters to the vast galactic web, might be the unfolding of a story that was written long ago on a flat surface at the edge of the universe. Are we living inside the most complex hologram imaginable? If our reality is a holographic projection, what is the projector itself made of? The answer might lie in a concept so turbulent it redefines the very idea of emptiness. At scales a trillion times smaller than a proton, at the realm of the Planck length, the smooth stage of spacetime we take for granted dissolves into a state of ultimate chaos. This is John Wheeler's Spacetime Foam, a seething, effervescent sea of geometry. Here, the energy of quantum fluctuations is so unimaginably violent that it does not merely create virtual particles. It twists and warps the fabric of reality itself. In this frenzied foam, tiny wormholes constantly blink into existence, connecting distant points for a fleeting instant before snapping shut. Microscopic virtual black holes form and evaporate in a furious cycle of creation and annihilation. The very concepts of before and after, here and there, lose their meaning in this quantum tempest. It is a bubbling broth of spacetime itself, forever in flux, yet we experience none of this chaos. The spacetime we move through feels continuous and smooth, like the surface of a calm ocean. That is because the foam operates at such an infinitesimally small scale that its turbulence is averaged out over the vast distances we can perceive. The wild jitters are hidden from our view, much like the churning molecules that make up the still surface of a lake. This foamy nature of reality is not just a curious detail. It might be the crucial bridge to the holy grail of physics, a theory of quantum gravity. Einstein's general relativity describes gravity as the smooth curvature of spacetime on large scales, while quantum mechanics governs the frantic probabilistic world of the very small. The two theories are mathematically incompatible, but spacetime foam offers a potential reconciliation. In this picture, gravity is not a fundamental force. Instead, it could be an emergent property, a collective outcome of the statistical average of all these churning quantum geometries, all these tiny wormholes and fluctuating curvatures. The smooth gravitational field we measure would be the final result, like the temperature of a gas emerging from the average motion of countless molecules. The foam is the missing link, the quantum description of gravity's underlying mechanics. So the next time you look up at the seemingly serene night sky, remember that you are gazing out from a reality built upon a foundation of ultimate turmoil. The stage upon which the cosmic drama plays out is not a rigid platform. It is a living, breathing, and frothing quantum sea, and its restless energy might just be the source of the force that holds our feet firmly on the ground. The chaotic foam of spacetime is a theoretical whirlwind, but we can actually reach out and touch the force of quantum fluctuations in a laboratory. This is the Casimir Effect, a tangible whisper from the quantum world. Picture a perfect vacuum completely empty of all air and particles. Now, place two incredibly smooth, uncharged metal plates so that they are perfectly parallel and extremely close together, only a few millionths of a meter apart. According to classical physics, with no air pressure and no electrical charges, nothing should happen. They should just sit there, but they do not. In reality, the plates experience a faint but measurable force pulling them together. What is pushing them? The answer lies in the nature of the quantum vacuum itself. We know that empty space is not truly empty, but a seething sea of virtual particles flickering in and out of existence. These fluctuations can be thought of as waves, and like any waves, they can only exist if they fit perfectly between the plates. Only certain wavelengths, specific frequencies of this quantum energy, are permitted in the narrow gap. Outside the plates, however, there are no such restrictions. Every possible wavelength of fluctuation can and does exist. This creates a profound imbalance. The relentless pressure from the riot of quantum fluctuations outside the plates is greater than the limited pressure from the restricted fluctuations between them. The result is an inward push, a quantum-induced force that squeezes the plates together. It is as if the vibrant energy of nothingness itself is hammering on the outside of the plates, forcing them to close. The Casimir Effect is not just a curious prediction, it has been confirmed by multiple precise experiments. It stands as one of the most direct and compelling pieces of evidence that quantum fluctuations are real physical phenomena, not just mathematical abstractions. We are not merely imagining a seething vacuum, we can measure its push. This simple experiment with two metal plates provides a stunning bridge between the abstract quantum realm and our tangible reality. If the vacuum can push plates together, what other invisible forces is it exerting on the fabric of the cosmos? That gentle pressure of the Casimir effect proves the vacuum is alive with energy, but what if motion itself could change the very nature of that emptiness? The Unruh Effect proposes a reality where an astronaut accelerating at a tremendous rate through what seems to be pure, empty space would not feel a cold void. Instead, they would find themselves enveloped in a warm bath of particles. To this accelerating observer, the vacuum would feel hot. Yet, for another observer floating nearby at a constant, steady speed, that same patch of space would register as completely empty and frigid. Both are correct from their own perspectives. How can this be possible? The secret lies in how acceleration interacts with the quantum field. Think of the quantum vacuum not as a still pond, but as a field buzzing with invisible, virtual vibrations. When you are moving at a constant velocity, you glide smoothly through this field, unable to detect these fleeting fluctuations. But if you accelerate, you are no longer gliding. You are shaking, jostling the quantum field with your motion. This violent shaking has a profound effect. It stirs up the virtual particles, imparting enough energy to them to cross the threshold from potential to real. The vacuum for the accelerating observer effectively boils. The faster the acceleration, the more violent the shaking, and the hotter the perceived temperature of this particle bath becomes. This bizarre phenomenon forges a deep and unexpected link between acceleration, temperature, and gravity. Einstein's principle of equivalence tells us that standing still in a gravitational field, like on the surface of the Earth, is physically equivalent to being in an accelerating rocket in empty space. If acceleration makes the vacuum appear hot, then gravity itself should also create heat. This stunning connection is the very bridge that led Stephen Hawking to his revolutionary prediction. He realized that the immense gravitational pull at the edge of a black hole, its event horizon, should act as a constant, ultimate acceleration. Just as our accelerating astronaut shakes particles from the vacuum, the black hole's gravity would shake pairs of virtual particles into existence right at its boundary. In most cases, these particle pairs would annihilate each other in a flash. But if one particle falls into the black hole, its partner can escape, carrying away energy. To an outside observer, this stream of escaping particles looks exactly like heat radiating from a hot object. This is Hawking radiation. So the Unruh Effect teaches us that our experience of reality is deeply personal, shaped by our own motion. The cold, empty void for one traveler is a warm, particle-filled sea for another. It suggests that the concepts of something and nothing are not absolute, but are relative to our journey through the cosmos. What else might be hiding in the vacuum, waiting for the right kind of motion to bring it to life? Stephen Hawking took the strange heat of the accelerating vacuum and applied it to the most extreme gravitational environment imaginable. His theory of Hawking radiation reveals that black holes are not eternal prisons, but are slowly leaking energy back into the cosmos. Picture the violent churn of spacetime foam magnified at the very edge of a black hole, the event horizon. Here, the pull of gravity is so immense that it constantly shakes the quantum fields, stirring up pairs of virtual particles. Normally, these particle and antiparticle pairs would annihilate each other in an instant, returning their borrowed energy to the vacuum. But at the precipice of the event horizon, a cosmic theft can occur. one particle of the pair might fall across the boundary, forever lost to the black hole's interior. Its partner, however, is now stranded outside, its debt to the universe unpaid. With its partner gone, this lone particle can no longer annihilate. It is promoted from a fleeting virtual flicker into a real particle, carrying real energy away into the universe as radiation. This is Hawking radiation. There is a profound cost for this process. The energy for creating this real particle does not come from nothing. It is extracted from the black hole's own gravitational field. To balance the cosmic books, the black hole must lose a tiny amount of mass. This means that over astronomical timescales, a black hole that is not feeding on new matter will slowly shrink, evaporating particle by particle back into the universe. The smaller the black hole, the stronger the gravitational gradient at its event horizon, and the hotter it glows with Hawking radiation. A stellar mass black hole is so cold it barely radiates, but a tiny, primordial black hole could shine with intense heat before vanishing in a final, explosive flash. This single, elegant idea ties together three great pillars of physics. It uses quantum field theory to explain the particle pairs, general relativity to describe the intense gravity, and thermodynamics to define the black hole's temperature and entropy. Hawking radiation transformed black holes from simple gravitational sinks into complex thermodynamic objects that possess temperature and eventually die. It suggests that information, the blueprint of everything that falls in, might not be lost forever but could be encoded in this escaping radiation, a puzzle that physicists are still working to solve. If even the darkest objects in the universe are slowly fading, then nothing, it seems, is truly permanent. The slow evaporation of black holes hints at a cosmos in constant flux, but what if our entire universe is just one fading bubble in an infinite cosmic foam? The theory of eternal inflation takes the concept of the Big Bang's rapid expansion and projects it onto an unimaginably vast canvas. In this picture, the initial inflationary period that shaped our universe never truly stopped. Instead, it continues forever in a background hyperspace, a raging ocean of inflating energy. Our observable universe is just one lucky region where this inflation decayed, its energy converting into the hot soup of particles and radiation that became our Big Bang. We live inside this stabilized bubble, a calm pocket in an eternally storming sea. But what creates new bubbles, the trigger, is quantum fluctuation. In the churning, inflating background, random quantum jitters can cause tiny pockets of the inflattened field to suddenly drop to a lower energy state. It is like a random air bubble forming in a pot of boiling water. When this happens, that tiny patch stops inflating violently and forms a new, stable bubble universe. This process, called bubble nucleation, is happening endlessly. Each new bubble universe spawns with its own random set of physical constants. The strength of gravity, the mass of an electron, the number of spatial dimensions, all could be different in each one, determined by the chaotic quantum conditions of its birth. In this infinite multiverse, every possible combination of physical laws is realized somewhere. This provides a potential answer to one of science's most profound questions: why is our universe so perfectly fine-tuned for life? If the strength of the dark energy driving cosmic expansion were just slightly stronger, galaxies could never have formed. If the nuclear force were a fraction weaker, hydrogen would be the only element and stars would never shine. The list of these precise, life-permitting values is long and seemingly miraculous. The multiverse theory offers a staggering explanation. There is no fine-tuning. We simply find ourselves in one of the rare bubbles where the cosmic lottery produced constants that allow for stars, planets, and life to emerge. In the overwhelming majority of other universes, the conditions are either too chaotic or too sterile for anything interesting to happen. We do not observe a designed cosmos, we observe the only kind of cosmos we could possibly exist within. This idea transforms our universe from a singular creation into a single leaf on an infinite tree of reality. The quantum fluctuations that seeded our galaxies are the same gentle tremors that, in the wider multiverse, continuously give birth to entirely new cosmic realms, each with its own unique story and its own ultimate fate. Are we living in just one room of a cosmic mansion with an infinite number of doors? This cosmic multiverse of endless possibilities is built upon a vacuum simmering with energy, and that same energy may be writing the final chapter for our own universe. We now confront one of the most pressing mysteries in cosmology, the identity of dark energy. This mysterious force is causing the expansion of our universe to accelerate, pushing galaxies apart at an ever-increasing rate. A leading candidate for this cosmic repulsion is the energy of the quantum vacuum itself. The logic seems beautifully simple. If empty space is truly filled with a seething sea of quantum fluctuations, then that seething must carry energy, and that energy should exert a gravitational effect. In Einstein's theory of general relativity, energy, in any form, influences the curvature of spacetime. The vacuum energy, with its negative pressure, would naturally produce a repulsive gravitational force, acting like a cosmological constant that drives the cosmos apart. This would be the ultimate triumph for quantum fluctuations, casting them not just as the architects of cosmic structure, but also as the pilots steering the entire fate of the universe. Yet this elegant idea slams directly into the vacuum catastrophe we encountered at the very beginning. The calculated energy density of the quantum vacuum is about 120 orders of magnitude too large. If the vacuum energy were that strong, the universe would have been ripped to shreds in its infancy. The observed acceleration driven by dark energy is real, but incredibly, almost impossibly weak in comparison to the theoretical prediction. This is not a small error, it is a screaming contradiction. How can the vacuum energy be both unimaginably powerful and yet almost perfectly silent? This colossal mismatch forces physicists to consider radical alternatives. Perhaps our understanding of gravity is incomplete on cosmic scales. Modified theories of gravity, which change how the force behaves over vast distances, could explain the cosmic acceleration without needing any dark energy at all. In these models, the subtle effects of quantum fluctuations might combine in unexpected ways to alter gravity itself, producing the illusion of a repulsive force. Another possibility is that the quantum vacuum is far more complex than we thought. Maybe different fields and their fluctuations cancel each other out with near-perfect precision, leaving behind only the faintest whisper of energy that we now detect as dark energy. This would require a level of fine-tuning that seems miraculous, a cosmic coincidence of breathtaking proportions. Or perhaps we are seeing the first evidence of a new, yet undiscovered physical field, one whose quantum jitters are perfectly calibrated to drive our universe's gentle acceleration. The search for an answer is one of the greatest quests in modern science. Whether dark energy is the muted voice of the quantum vacuum or the signature of entirely new physics, its discovery has irrevocably linked the fate of the cosmos to the restless energy of nothingness. The same tiny tremors that gave us stars may ultimately determine whether our universe expands into an endless, cold, and lonely future. The gentle whisper of dark energy that guides our cosmic fate brings us to a deeply personal and controversial question. Why does our universe seem so perfectly tailored for our existence? This is the anthropic principle, an idea that turns the mystery of our fine-tuned cosmos inward. It suggests a simple yet staggering reason we observe the specific quantum fluctuations we do. We are here to see them. The primordial seeds that grew into galaxies, stars, and planets could only have produced observers in a universe where those seeds were, quite literally, just right. If the initial quantum jitters had been a little stronger, the universe would have collapsed back on itself immediately after the Big Bang. If they had been a little weaker, matter would have spread out too thinly, and gravity could never have pulled together the first stars. Our cosmic neighborhood and our very presence within it depends on a narrow, golden window of fluctuation strength. This logic can feel like a profound insight or a complete cop-out. Is it a legitimate scientific explanation or merely a tautology, a circular argument that we see what we see because we are here to see it? The principle gains real power when combined with the theory of the multiverse. In an eternally inflating cosmos where countless bubble universes are constantly born with random physical properties, the anthropic principle becomes a powerful selection effect. We do not live in a special universe, we live in a typical one, but only typical for universes that contain life. The vast majority of universes in the multiverse would have fluctuation patterns that are either too wild or too calm to allow for galaxies and complex chemistry. They are cosmic dead ends, empty or short-lived. We, by necessity, find ourselves in one of the rare, lucky bubbles where the quantum lottery produced a winning ticket. The precise pattern of hot and cold spots in the cosmic microwave background, the very blueprint for our existence, might not be a product of fundamental law, but a simple result of cosmic chance. So, did our universe win the ultimate lottery? The answer depends on whether you see our reality as a unique creation or a single fortunate roll of the quantum dice in a casino with an infinite number of tables. Our universe should not exist. In the fiery forge of the Big Bang, matter and antimatter should have been created in perfectly equal amounts. For every proton born, an antiproton should have emerged. For every electron, a positron. And according to the laws of physics, when these identical but oppositely charged particles meet, they annihilate each other in a flash of pure energy, leaving behind nothing but light. A perfectly symmetrical universe would have been a brief, brilliant flash, followed by an eternal, featureless darkness. Yet here we are, in a cosmos filled with galaxies, stars, and planets, all made of matter. The antimatter has almost entirely vanished. This is one of cosmology's most profound puzzles, and the answer may be written in the subtle rhythms of the early universe's quantum noise. This leads us to the theory of Sakharov oscillations and the genesis of matter itself. The physicist Andrei Sakharov proposed 3 essential conditions needed to create a matter-dominated universe from a symmetrical beginning. First, there must be a process that treats matter and antimatter differently, a phenomenon known as CP violation, where the laws of physics are not quite identical for particles and their mirror image antiparticles. Second, this process must occur when the universe is far from thermal equilibrium, a state of chaotic, rapid change where such an asymmetry can be frozen into the fabric of reality before it smooths itself out. And third, there must be interactions that can change the total number of particles, allowing a net surplus to be created. Quantum fluctuations provide the crucial stage for this cosmic drama. In the unimaginable heat of the first moments, the universe was a seething, boiling soup of quantum fields. Within this chaos, fluctuations were constantly creating pairs of particles and antiparticles. Now imagine these pairs not just appearing and vanishing, but oscillating, rapidly switching between matter and antimatter states, like a coin spinning in midair. This is the realm of Sakharov oscillations. Due to CP violation, the spinning coin was ever so slightly weighted. The oscillation from matter to antimatter was not perfectly symmetrical with the oscillation from antimatter back to matter. In a universe out of equilibrium, cooling and expanding too rapidly for balance to be restored, this tiny bias was amplified. For every 1,000,000,001 oscillations that resulted in a matter particle, only 1,000,000,000 resulted in an antimatter particle. It was a minuscule imbalance, a 1 in 1,000,000,000 preference, but it was enough. When the great annihilation came, nearly all particles met their opposites and vanished. But that 1 in 1,000,000,000 surplus of matter particles had no partners to annihilate with. They were left behind, the lonely survivors of a cosmic war of attrition. Every atom in your body, every star in the night sky, is a relic of that ancient quantum-imprinted surplus. We are the leftover ash from a fire that almost completely consumed its own fuel. The existence of our material world hinges on a quantum whisper, a barely perceptible tremor in the laws of symmetry that decided, once and for all, that something would come from almost nothing. That 1 in a billion surplus of matter might be the foundation of our reality, but how does any single quantum possibility solidify into the actual world we experience? One of the most mind-bending answers comes from the transactional interpretation of quantum mechanics. This theory reframes the entire quantum dance not as a game of chance, but as a cosmic marketplace of handshakes between the past and the future. In this view, a quantum event begins when a particle, like an electron, sends out an offer. This offer is a wave that travels forward in time as we would normally expect. But it also sends out an identical wave that travels backward in time. Think of it as an invitation sent out to the entire timeline, from the beginning of the universe to its very end. These backward-traveling waves are called advanced waves, and they are a crucial, if bizarre, part of the proposal. Now, imagine a particle detector in the future, ready to receive that electron. It responds to the initial offer. It sends its own confirmation wave backward in time, an echo that perfectly matches the original advanced wave. When the offer wave from the past and the confirmation wave from the future meet, they form a resonant handshake, a completed transaction. It is this closed loop in time that gives the quantum fluctuation its definite outcome. The electron is no longer a cloud of possibilities. It becomes a real particle detected at a specific point in space and time. The entire process resembles a cosmic auction. The past shouts out an offer and the future places a bid. Only when the bid is accepted does the reality of the transaction become settled. This interpretation provides a stunningly elegant explanation for the famous double-slit experiment, where a single particle seems to pass through 2 slits at once, interfering with itself. In the transactional view, the particle sends out offer waves through both slits. The detector on the other side then sends confirmation waves back through both paths. The transaction that is ultimately completed is the one where the waves from the past and future reinforce each other most strongly, creating the familiar interference pattern. The other possible paths simply fail to secure a deal and never become real. This means the quantum fluctuations we have been exploring, from the vacuum's seething energy to the primordial seeds of galaxies, were not random accidents. Each one was a transaction confirmed by the future state of the universe itself. The cosmos we see is the result of trillions upon trillions of these handshakes across time, a universe built on agreements between what was and what will be. It forces us to ask a profound question. Does the future we are moving toward play an active role in creating the present we now inhabit? But what if the future is not shaping the present? What if the quantum world only appears random because we are blind to its deeper, hidden mechanics? This brings us to a theory that dares to restore a sense of concrete reality to the quantum realm. It is called pilot wave theory, or the de Broglie-Bohm theory, and it proposes that particles are not ghostly probability clouds. They are real, tiny objects with definite positions at all times, guided by an invisible force. Imagine a tiny boat floating on a restless ocean. The boat itself has a specific location, but it is pushed and pulled by the waves surrounding it. In this analogy, the boat is the particle, like an electron. The ocean is the pilot wave, a real, physical field that guides the particle's path. The particle does not exist in many places at once. It has a single, precise trajectory, but that trajectory is completely determined by the shape and motion of its guiding wave. In this view, the famous quantum fluctuations are not evidence of true randomness. They are a result of our ignorance. We cannot see the detailed structure of the pilot wave or the particle's exact starting position. These are the hidden variables, the unseen factors that make the outcome seem unpredictable to us, even though it is perfectly determined. This stands in stark contrast to the standard Copenhagen interpretation, which states that particles do not have definite properties until they are measured, and that probability is a fundamental, irreducible feature of nature. Pilot wave theory rejects this. It says the universe is deterministic. If you knew the exact state of every pilot wave and every particle, you could, in principle, predict every single quantum event with perfect accuracy. The apparent randomness of which path a particle takes, or when a radioactive atom decays, is just a mask for a deeper, hidden order. This idea extends to the vacuum itself. The seething sea of virtual particles could be seen not as random creations from nothing, but as the visible froth on top of deeply structured, deterministic pilot waves churning beneath the surface. Even the primordial quantum jitters that seeded the galaxies might have been the inevitable result of a specific, if unknowable, initial configuration of the cosmic pilot wave. While it has its own mathematical challenges, pilot wave theory offers a profoundly different philosophical stance. It suggests a universe that is real and definite whether we are looking or not, a cosmos where the unsettling quantum dice are not rolled, but where every outcome was always written in the waves. The deterministic order of pilot wave theory offers a comforting solidity, but what if the exact opposite is true? What if every single quantum fluctuation, every random flicker of a particle, does not settle into one reality but instead creates them all? This is the many worlds interpretation, a vision of reality so vast it stretches the mind to its breaking point. In this framework, the universe is not a single linear timeline. It is an ever-branching tree with new limbs sprouting from every possible quantum event. Think of a single electron spin. In our everyday experience, we measure it and find it pointing either up or down. The standard view is that the act of measurement forces a random choice, but many worlds proposes something far more radical. There is no choice. At the moment of measurement, the entire universe splits in two. In one branch, you see the electron spin up and record that result. In the other, an identical version of you sees the electron spin down. Both outcomes are equally real. Both US are conscious and certain of their result. They simply now inhabit separate, parallel universes that can never again communicate. This branching is not limited to laboratory experiments. It happens constantly, everywhere, with every quantum fluctuation that defines our reality. The primordial quantum jitter that placed a galaxy here instead of their created two cosmic histories. The random decay of a single radioactive atom in a distant star spawns new universes with each possible moment of decay. Every time you make a decision, even a small one, the process is rooted in quantum events in your brain. Each possible action is realized in a different branch of the multiverse. There is a universe where you turned left instead of right, where you spoke instead of staying silent, where every road not taken in this world is in fact a well-traveled highway in another. This interpretation does away with the idea of probability altogether. The quantum dice are not rolled to pick one outcome. They are rolled, and every single face lands simultaneously, each in its own newly minted reality. The reason we perceive a 50-50 chance for an electron spin is not because the outcome is random, but because there are two versions of us, each living in a universe where one specific outcome occurred with absolute certainty. The implications are staggering. The infinite multiverse of eternal inflation is populated not just by universes with different physical constants, but by an infinity of universes nearly identical to our own, differing only in the result of one single quantum coin toss a moment ago. In this cosmic panorama, every possible history plays out. There is a branch where the dinosaurs never went extinct, a branch where ancient Rome discovered steam power, a branch where you are reading this script in a different language. Our specific timeline, with all its unique joys and sorrows, is not special. It is just one thread in an immeasurably vast tapestry of what could be. This forces a profound and personal question. If a near infinite number of you are living out every possible version of your life, what does that say about the choices you make today? Are they uniquely yours, or are they simply the path this particular version of you was destined to walk? The vast branching of the many worlds interpretation offers a dizzying array of realities, but it still relies on a stage of continuous space and time. What if that stage itself is an illusion? Our next theory proposes that space and time are not smooth and endless, but are made of tiny, indivisible pieces. This is loop quantum gravity, and it rewrites the origin story of our cosmos. In this framework, the fabric of spacetime is woven from a network of finite loops, a spin network where each thread carries a tiny, quantized unit of area or volume. Picture the smooth surface of a pond. Up close, it seems continuous, but we know it is made of countless discrete water molecules. Loop quantum gravity suggests spacetime is the same, composed of fundamental grains at the smallest possible scale, the Planck length. This granular structure has a profound consequence for the universe's very beginning. In classical cosmology, the Big Bang is a singularity, a point of infinite density and temperature where the laws of physics break down entirely. But in loop quantum cosmology, the sister theory, there is no such singularity. The quantum nature of spacetime acts as a cosmic repulsive force. As we rewind time and the universe contracts to an incredibly dense state, this repulsion from the granular geometry becomes overwhelmingly powerful, preventing a collapse into infinity. Instead of a big bang from nothing, the universe undergoes a big bounce. Our expanding cosmos could be the rebound from a previous universe that had collapsed under its own gravity. We are not the first chapter, but merely one cycle in a potentially endless cosmic rhythm. So where do quantum fluctuations fit into this granular picture? In this theory, the primordial seeds for galaxies are not just random jitters in a field. They are vibrations in the very fabric of the spin network, tiny imperfections in the weave of spacetime itself. The quantum fluctuations that seeded our entire cosmic structure are the quantum uncertainties inherent in the discrete geometry of the universe. Because space and time are quantized, they have a fundamental fuzziness, a built-in level of noise that was imprinted on the cosmos as it emerged from its bounce. This provides a completely new context for understanding the origins of everything. The slight variations in density that grew into galaxies were not stamped onto a smooth, pre-existing stage. They were born from the quantum-grained nature of the stage as it was being built. This theory elegantly avoids the troublesome singularities of classical physics and paints a picture of a cyclic or eternal universe, where each great collapse gives birth to a new expansion through the quantum properties of spacetime itself. The cosmos becomes a phoenix, forever dying and being reborn from its own ashes, with the quantum tremors of its geometry writing the blueprint for each new incarnation. While one universe dies in cold, empty silence, another is born in a blaze of heat. Roger Penrose's conformal cyclic cosmology proposes an endless cosmic cycle where the death of one universe becomes the Big Bang of the next. In this breathtaking vision, time itself is not a single line from a beginning to an end, but an infinite series of cosmic seasons, each called an aeon. Our universe is just one aeon in this endless chain. The key to this rebirth lies in a strange symmetry that emerges at the very end and the very beginning of time. In the far, far future, when the last black hole has evaporated and the universe has expanded into a vast, cold void containing only the faintest radiation, something remarkable happens. All particles will have decayed, and all that remains is a sea of low-energy light. In this state, the universe loses all sense of scale. There is no ruler to measure distance, no clock to tick off time. A universe of immense size and a single, lonely photon become indistinguishable in a mathematical sense. This property is called conformal symmetry, a perfect scale invariance where the concepts of big and small simply cease to have any meaning. At this point of infinite smoothness, the end of our eon can be seamlessly attached to the beginning of the next. The cold, silent, and infinitely large end of one universe becomes the hot, dense, and infinitely small Big Bang of the next. But how could anything carry over from one eon to another? The answer lies in gravitational waves. When supermassive black holes collide, they send ripples through the fabric of spacetime, vibrations that travel across the cosmos. According to Penrose, these ripples are not lost in the transition between eons. Because they are made of pure geometry, they can survive the conformal rescaling, the mathematical process that transforms the end of one eon into the start of another. The information encoded in these gravitational waves, the echoes of ancient cosmic collisions, could be imprinted onto the new eon's initial conditions. This is where quantum fluctuations re-enter the story in a profound way. In the new eon, these transmitted gravitational waves would manifest as slight variations in the initial density of the universe. They would act as the primordial seeds, the very same kind of quantum jitters that we believe sparked the formation of galaxies in our own cosmos. In this cyclical model, the quantum fluctuations that define each new universe are not entirely random. They are partially shaped by the gravitational memory of the previous eon's most violent events. The large-scale structure we see today, the distribution of galaxies and clusters, could be a faded fossil, a ghostly imprint of black hole mergers that occurred in a universe that existed before our own. Penrose and his colleagues have even searched for evidence of this, claiming to have found faint, concentric circular patterns in the cosmic microwave background, which they call Hawking points. These would be the smeared-out signatures of the final, explosive evaporation of supermassive black holes from the previous eon. This claim remains highly controversial, with many scientists arguing the patterns are statistical anomalies. Yet the idea itself is staggering. The universe may not be a one-time event, but an eternal, self-renewing process. The quantum seeds from which our world grew might be whispers from a forgotten past, and the collisions of dark giants in our own future could be laying the groundwork for a cosmos yet to be born. Are we living in the aftermath of another universe's death, and are we, in turn, creating the blueprint for the next? Roger Penrose's cyclical cosmos suggests information might echo between eons, but this leads us back to a fiery debate at the heart of black hole physics. The black hole information paradox forces us to confront a terrifying possibility. When something falls into a black hole, every bit of information that defined it, from its atomic structure to its spin, seems to vanish forever once the black hole evaporates through Hawking radiation. This violates a sacred principle of quantum mechanics, the law of unitarity, which states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased from the universe. The core of the problem lies in the very nature of Hawking radiation. This radiation is thermal. It is random heat generated by the quantum fluctuations at the event horizon. It carries no specific details about the individual particles that fell in. If you burn a book, you can no longer read its words, but in principle, if you could collect every single ash particle and trace every photon of light and heat, you could reconstruct the book. The information still exists, just in a vastly more complicated form. Hawking radiation, however, seemed to be a different kind of fire. It appeared to be purely random, offering no such path to reconstruction. The information about the book, the unique quantum states of every single atom that made up its pages, would be lost forever when the black hole finally pops out of existence. This paradox pits our two most successful theories against each other in a fundamental way. General relativity, which governs black holes, allows for information destruction. Quantum mechanics forbids it. One of them must break down. Proposed solutions are as radical as the problem itself. One idea is black hole complementarity. It suggests that from the perspective of an outside observer, the information never actually crosses the event horizon. Instead, it is scrambled and encoded onto the fluctuating surface of the horizon itself, and then slowly radiated back out via the Hawking radiation. However, from the perspective of an astronaut falling in, they would cross the horizon smoothly with no drama, carrying the information into the black hole's interior. Both perspectives are correct within their own frames, but they can never be compared, preserving the consistency of physics. This solution avoids contradiction by making the inside of the black hole and its horizon complementary descriptions of the same reality, like the wave and particle nature of light. A more violent alternative is the firewall hypothesis. It proposes that to prevent information from being duplicated, the event horizon is not a smooth gateway. It is a blazing wall of high-energy particles, a literal firewall that would instantly incinerate anything falling in. In this picture, the quantum fluctuations at the horizon are not gentle creators of particle pairs, but an intensely energetic barrier that protects the laws of quantum mechanics by destroying the infalling object before its information can be cloned. Then there is the profoundly elegant ER=EPR conjecture. It proposes that the entangled particle pairs created by quantum fluctuations at the horizon are not just connected by quantum links. They are physically connected by tiny, microscopic wormholes known as Einstein-Rosen bridges. When one particle falls in and its partner escapes, they remain connected through a space-time tunnel. The information of the infalling particle does not reside in the black hole or on the radiation, but in the geometric connection between them. The interior of the black hole might be nothing more than the other end of a vast web of these wormholes, linking it to all the Hawking radiation it has ever emitted. In this view, information never falls into a black hole at all. It simply takes a different path through the quantum gravitational plumbing of spacetime. Each of these solutions attempts to rescue information from the void, redefining the role of quantum fluctuations from agents of destruction to potential guardians of cosmic memory. The fate of a single bit of information, it seems, holds the key to unifying our understanding of the entire universe. The very fabric of reality might be stitched together by threads of pure connection. The ER=EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, offers a breathtakingly geometric vision of the quantum world. It boldly states that the strange, instantaneous link between two entangled particles, known as an EPR pair, is not a mysterious, spooky action at a distance. It is a physical bridge, a microscopic wormhole known as an Einstein-Rosen bridge. Think of two coins, one on Earth and one on Mars, that are forever linked so that flipping one instantly determines the face of the other. The standard quantum view treats this as a fundamental, non-local connection, but ER=EPR suggests there is no spooky action because the coins are not truly separate. A tiny, traversable tunnel, a wormhole, physically connects them. The entanglement itself is the geometric fabric of that tunnel. This radical idea reimagines the quantum fluctuations at the heart of our story. Every time the vacuum flickers with a pair of virtual particles, it is not just creating two disconnected entities. It is, for an infinitesimal moment, pinching the fabric of spacetime to form a microscopic Einstein-Rosen bridge between them. The particles are born connected by a tiny thread of spacetime geometry. When they annihilate, the bridge collapses. The vacuum of space, then, is not just a seething sea of particles. It is a foaming ocean of ephemeral wormholes, constantly being woven and unwoven by quantum uncertainty. This provides a stunningly elegant potential solution to the black hole information paradox. Recall the problem: information falling into a black hole seems lost forever when the whole evaporates. But if every particle of Hawking radiation is entangled with a partner inside the black hole, then ER=EPR tells us they are connected by a wormhole. The information of the infalling matter does not reside trapped inside the black hole, nor is it lost. It is encoded in the vast, complex network of wormholes that link the black hole's interior to all the Hawking radiation it has ever emitted. The black hole is not a prison, but a knot in the quantum gravitational fabric of space-time, with its contents safely stored in the connections to the outside universe. This transforms our view of reality's foundation. The smooth, continuous space-time we experience may be an emergent illusion, a collective average of an unimaginably dense network of quantum entanglement. Every atom, every star, every one of us is embedded in a cosmic web of microscopic wormholes, a tapestry woven from a trillion quantum handshakes. Is the universe we see merely the visible texture of this hidden, deeply connected geometry? This geometric object, the amplituhedron, turns our entire narrative on its head. It is a jewel-like mathematical shape that calculates how subatomic particles scatter and interact after a collision, but it does so with a breathtaking omission. The calculation requires no mention of space-time, no quantum fields, and no virtual particles flickering in and out of existence. The endless dance of quantum fluctuations, the very foundation we have explored, simply does not appear in its geometry. The amplituhedron computes the outcomes of particle physics perfectly, yet it acts as if space, time, and uncertainty are not fundamental ingredients of reality. How can this be possible? It suggests that the locus of locality, the rule that objects can only be influenced by their immediate surroundings, is an illusion. The amplituhedron's calculations are inherently non-local, treating particles and their interactions as a unified whole, independent of where or when they occur. In this view, the seething quantum foam and the virtual particles of the Casimir Effect are not the primary reality. They are a consequence, a clumsy translation of a deeper, more elegant mathematical truth into the language of space-time that our brains have evolved to understand. The universe might not be built from tiny, jittering bits of energy in a vacuum. Instead, it could be a consequence of a profound, geometric logic that exists beyond our familiar concepts of here and there, then and now. So are the quantum fluctuations we have been following simply shadows on a cave wall, cast by the turning of a perfect, silent, and timeless geometric form. That silent, geometric perfection of the amplituhedron hints at a reality built on pure mathematics, a notion that leads to one of the most provocative theories of all. What if these mathematical rules are not just a description of reality, but the very source code of a simulation? The simulation hypothesis proposes that our universe, with all its galaxies, stars, and conscious life, is not base reality. It is an elaborate construct, a digital simulation running on a computer of unimaginable power in a higher-level existence. And the quirky, discrete nature of quantum mechanics provides some of the most compelling clues. Think about the fundamental limit of the Planck length, a distance so small that our concept of space breaks down. This could be the pixel size of the simulation, the smallest possible unit of resolution in the cosmic display. Just as a digital image becomes blocky when you zoom in too far, space-time itself might reveal its granular, computational nature at this infinitesimal scale. Quantum fluctuations, then, are not random jitters of an energy field. They could be the background processing noise of the simulation itself. Every time a virtual particle pair flickers into existence, it might be the result of a random number generator in the code, a computational shortcut to simulate the average behavior of a vacuum without calculating every single detail of a more complex underlying reality. The probabilistic nature of quantum events, where outcomes are not determined until observed, fits perfectly with a simulation designed to save processing power. Why render the entire universe in perfect detail all the time? It is far more efficient to only calculate the definite properties of a system, like the spin of an electron, at the moment it is measured, a technique known in computing as lazy evaluation. This need for efficiency could explain some of the universe's deepest mysteries. The speed of light, the universe's ultimate speed limit, might be the clock rate of the central processing unit, the maximum speed at which information can be transmitted and processed between different parts of the simulation. Even the bizarre results of the double-slit experiment, where a particle seems to know if it is being watched, could be a simple optimization. The program does not need to calculate a definite path for the particle until the data is requested by a conscious observer, an entity complex enough to require a rendered outcome. If this is true, we might one day find evidence of the simulation in the form of glitches or rounding errors in the laws of physics. Perhaps certain physical constants, which seem so finely tuned, are actually hard-coded variables that were set by the programmers. Maybe we could detect anomalies in high-energy particle collisions that reveal the limits of the simulation's rendering engine, or find strange statistical patterns in cosmic rays that betray the use of a pseudo-random number generator. The very quantum fluctuations that seeded our galaxies could be the digital static of a reality not quite as solid as it seems. This forces a deeply philosophical question. If we are living in a simulation, are the programmers themselves living in a simulated world, in an infinite regress of realities? Or is our consciousness, our ability to question our own existence, the most compelling argument that we are more than just lines of code? But what if the dice are not rolled at all? Stochastic electrodynamics dares to suggest that the quantum world's famous randomness is not a fundamental feature of reality, but a simple consequence of something we have missed. This theory returns to a classical picture, one where particles are real objects with definite paths, not ghostly probability clouds. In this view, the entire universe is filled with a real, physical, and timeless background sea of energy, the zero-point field. This is not a field of virtual particles, but a classical electromagnetic field in a state of constant, random fluctuation. Every particle, every electron, is constantly being jostled by this never-ending background static. Imagine a tiny boat on a stormy ocean. The boat has a definite location, but its path is wildly unpredictable because it is being battered by countless random waves from all directions. In stochastic electrodynamics, the electron is the boat, and the zero-point field is the stormy sea. Its seemingly random quantum behavior, including the jitters we call fluctuations, is not born from an inherent uncertainty in its nature. It is a direct, classical result of being constantly shaken by this hidden, energetic medium. This theory can reproduce many of the most baffling quantum effects without ever invoking wave function collapse or inherent randomness. The Casimir Effect, for instance, is perfectly explained. The metal plates simply block certain frequencies of this real background field, creating an imbalance in the radiation pressure that pushes them together. Even the stability of atoms finds a classical explanation. In the old planetary model, an orbiting electron should spiral into the nucleus as it radiates away energy. But in stochastic electrodynamics, the electron is constantly being pushed by the zero-point field. This incoming energy perfectly balances the energy it loses, creating a stable orbit. The electron's dance around the nucleus is not a probability orbit, but a dynamic equilibrium between radiation loss and energy gain from the hidden sea. This offers a profoundly more intuitive picture of the quantum world. There is no spooky action at a distance, no cats that are both dead and alive. There is only a particle with a real trajectory, doing its best to navigate a universe filled with an invisible, churning energy that guides its every move. The quantum fluctuations that built the cosmos would then be the large-scale echoes of this universal background noise. It makes you wonder, is the universe's quantum weirdness not a signature of fundamental randomness, but simply the visible tremor of a hidden ocean we have yet to fully chart? That hidden ocean of background noise might be the source of all motion, but motion requires time, and time itself may be the universe's greatest illusion. Our theories of reality are locked in a silent war over its very nature. Einstein's general relativity paints a breathtaking picture of a block universe, a static, four-dimensional tapestry where past, present, and future all exist simultaneously. In this view, time is just another coordinate, a dimension woven into the fabric of space-time. The flow of time, the feeling of a moving now, is a persistent human illusion. Yet our other great theory, quantum mechanics, is built upon change and probability. Its equations describe how systems evolve, how a particle's wave function spreads over time. It needs a clock to tick. This is the problem of time in quantum gravity, a fundamental conflict at the heart of physics. If we try to merge these two theories, the time variable simply vanishes from the core equations of quantum gravity. We are left with a timeless description of the universe, a frozen snapshot with no obvious way to generate the dynamic, flowing reality we all experience. So where does our undeniable sense of time come from? The answer might lie in the very quantum fluctuations we have been following. Time may not be a fundamental ingredient of the cosmos. Instead, it could be an emergent property, a collective behavior that arises from the statistics of countless quantum events. Think of the concept of temperature. A single molecule does not have a temperature. Temperature is a statistical property that emerges from the average kinetic energy of trillions upon trillions of chaotically moving molecules. In a similar way, the flow of time might emerge from the relentless churn and evolution of quantum fluctuations across the universe. The sequence of events we perceive as the past causing the present, and the present causing the future, could be a cosmic mirage generated by increasing quantum entanglement and the growing complexity of these fluctuations. Your internal feeling of time passing, the reason you remember yesterday but not tomorrow, might be a direct consequence of the universe progressing from a state of low quantum complexity to a state of high quantum complexity. In this picture, the cosmic clock began ticking with the first primordial quantum jitter. The initial state of the universe at the Big Bang was one of extraordinarily low complexity, a highly ordered state. As those initial fluctuations were stretched and amplified, they began to interact to become entangled with one another in increasingly complex ways. This growing web of quantum connections creates an arrow of time, a direction in which complexity and disorder increase. We perceive this increase as the unstoppable flow from past to future. So the quantum fluctuations that seeded galaxies are not just structures in space, they are the very ticks of the cosmic clock. Each virtual particle pair flickering in the vacuum, each new entanglement formed, is a tiny step in the universe's journey from simplicity to complexity. This suggests a staggering possibility. In a truly timeless reality, the entire history of the cosmos, from the Big Bang to the last black hole evaporating, just is. But our conscious journey through that frozen landscape, our lived experience of time, is a story written by the evolving, statistical dance of quantum uncertainty. Are we simply riding a wave of increasing complexity, mistaking its flow for the river of time itself? The quest to tame the vacuum's wild energy leads us to a theory of stunning elegance and profound consequence. Supersymmetry proposes a deep and hidden symmetry woven into the fabric of reality, one that could calm the furious quantum jitters of the Higgs field. This field is what gives fundamental particles their mass, but its own mass is incredibly delicate. Calculations show that quantum fluctuations from the virtual particles in the vacuum should violently interact with the Higgs, driving its mass to an astronomically high value. This would make particles like electrons impossibly heavy, preventing atoms and therefore life from ever forming. Supersymmetry offers a beautiful solution. It suggests that for every known particle, from electrons to quarks, there exists a hidden, supersymmetric partner. For an electron, there would be a selectron. For a quark, a squark, these superpartners would differ in a key property called spin. The magic happens in their interaction with the Higgs field. The quantum fluctuations from ordinary particles tend to push the Higgs mass upward. But the fluctuations from their superpartners would push it downward with an equal and opposite force. It is a cosmic balancing act, a perfect cancellation of quantum noise that would naturally stabilize the Higgs mass at the delicate, low value we observe. This makes the universe's viability not a miracle, but a natural consequence of a deeper symmetry. Beyond solving this puzzle, supersymmetry provides a breathtaking path toward the unification of nature's forces. At the incredibly high energies of the early universe, the electromagnetic, weak, and strong forces would merge into a single, unified force, but only if supersymmetry is there to guide the mathematics. It is a theory that promises order, stability, and unity, yet experiment has delivered a sobering challenge. The Large Hadron Collider, our most powerful microscope, has searched diligently for these superpartners. According to the simplest versions of the theory, they should have been produced in the collider's energetic collisions and revealed themselves. So far, they have not appeared. This absence places supersymmetry under immense pressure, forcing physicists to consider more complex and subtle versions where superpartners are too heavy for current machines to detect. Despite this, the core idea remains profoundly compelling. It represents a hope that behind the apparent chaos of the quantum foam lies a hidden structure of perfect balance, a symmetry so powerful it can quiet the vacuum's roar and weave the forces of nature into a single tapestry. If supersymmetry is real, then every particle we know has a hidden twin, a silent partner working behind the scenes to make our stable, material universe possible. Supersymmetry offers a beautiful vision of a balanced vacuum, but we must now return to the problem that defies all such elegance. The cosmological constant problem remains the single worst theoretical prediction in the history of physics. It is a screaming paradox that mocks our attempts to understand the quantum vacuum. Our theories suggest that the energy of empty space should be so immense it would rip atoms apart before they could ever form. Yet we measure a value for this vacuum energy, this dark energy that is almost zero, a whisper in a hurricane. The difference between prediction and reality is a number with over 120 zeros. This is not a small error. It is a fundamental failure, telling us that something is profoundly wrong with our understanding of quantum fields or gravity or both. How can the universe's most vibrant source of potential energy be so eerily quiet? One radical solution emerges from the labyrinth of string theory. This framework suggests that our universe is not unique. Instead, it is one of an astronomical number of possible universes, each with a different value for the cosmological constant. This is the string theory landscape, a vast cosmic terrain of possible physical laws. In this landscape, the value of the vacuum energy is not determined by a fundamental law. It is set by chance, a random outcome of how the extra dimensions of string theory are curled up and stabilized. Most of these universes would have a cosmological constant too large for any structure to form. They would flash into existence and immediately tear themselves apart or collapse. But in a tiny, tiny fraction of these possibilities, the numbers would, by pure chance, come out almost zero. Our universe, with its gently accelerating expansion, would be one of these exceptionally rare and habitable islands in the landscape. This is where the anthropic principle forcefully re-enters the story. We should not be surprised to measure a tiny cosmological constant, because we could not exist in any of the universes where it is large. Our presence here acts as a selection effect. We are not observing a finely tuned cosmos. We are simply living in one of the few cosmic environments where the quantum vacuum is quiet enough to allow for galaxies, stars, and planets to form. The vacuum energy is not fine-tuned for life. Life emerged only in a place where the vacuum energy was, by sheer accident, already fine. This line of reasoning is as controversial as it is compelling. To some, it feels like giving up on a fundamental explanation. To others, it is the only logical conclusion from the staggering numbers involved. Solving the cosmological constant problem is not just an academic exercise. It is the essential key to unlocking the true nature of quantum fluctuations. Are they truly random, or is their apparent value in our universe the result of a cosmic lottery we were destined to win? The answer will determine whether the vacuum's silence is a profound clue or the ultimate cosmic coincidence. Gravity might not be a fundamental force at all, but a cosmic mirage. Eric Verland's theory of emergent gravity proposes that what we feel as gravity is not a force transmitted by particles or a warp in space-time. It is an entropic force, a side effect of the universe's relentless drive toward disorder. Picture a polymer chain, a long, wiggly molecule suspended in a warm fluid. The chain does not stay straight. It constantly jiggles and folds into a tangled mess. This is not because some invisible force is pulling on it, but because there are astronomically more tangled, disordered states for it to occupy than ordered ones. The tendency to maximize entropy, a measure of this disorder, makes it coil up. The force you would need to apply to stretch it straight is not a fundamental force of nature. It is an entropic force, a direct consequence of the system seeking higher entropy. Verland suggests that gravity works in a similar way, but on a cosmic scale. The stage for this drama is the holographic principle we encountered earlier. Reality's information is stored on a two-dimensional surface, a holographic screen. The quantum fluctuations we have been following are the microscopic vibrations of the bits of information encoded on this screen. When a massive object, like a star or a planet, is present, it effectively displaces information, changing the entropy of the screen. The natural tendency for this system to maximize its entropy then generates an effective force that pulls other objects toward the massive one. We interpret this force as gravity. In this view, Einstein's general relativity, with its elegant curvature of space-time, is not the final word. It is an approximate, emergent description of this deeper, information-theoretic process. The quantum foam, the churning of virtual particles, is the visible signature of these microscopic degrees of freedom on the screen, constantly rearranging themselves, driving the universe toward greater disorder, and in the process, creating the illusion of a force that holds worlds together. So the apple that fell on Newton's head was not pulled by a fundamental force, but was pushed by the silent, statistical tendency of the cosmos to forget, to become more disordered. Is the force that binds the galaxies simply the universe's irresistible urge to forget its own structure? Our universe seems perfectly tuned for chemistry, but what if one of its fundamental forces simply went missing? A thought experiment called the weakless universe strips away the weak nuclear force, and the consequences are catastrophic for cosmic construction. Without this specific force, the universe would be a much simpler and ultimately sterile place. The weak force governs a process crucial to the life cycle of stars, beta decay, which allows neutrons to turn into protons and vice versa. This ability to change a particle's very identity is the key that unlocks the universe's chemical diversity. In the first few minutes after the Big Bang, during the period of primordial nucleosynthesis, protons and neutrons were rapidly combining to form the first atomic nuclei. In our universe, the weak force kept the population of neutrons and protons in a delicate balance, allowing a significant fraction of neutrons to be bound into stable helium nuclei. But in a weakless cosmos, that balance is shattered. Neutrons, unable to decay into protons, would remain frozen. They would rapidly all be locked up into the simplest possible nucleus, a diproton, a pair of protons that is violently unstable. Almost no helium would form. The universe would be left with a boring sea of hydrogen with no heavier elements to speak of. This means no carbon, no oxygen, no iron. There would be no raw materials for planets, no chemistry beyond the simplest molecules, and certainly no possibility for life. The very quantum fields that define our reality and the specific spectrum of their fluctuations had to possess exactly the right properties to allow the weak force to exist and operate as it does. The fact that our quantum vacuum produces fluctuations that permit this specific force is not a minor detail. It is the foundational requirement for a cosmos that can eventually become interesting. This thought experiment forces a stark realization. The quantum blueprint of our universe did not merely allow for stars and galaxies. It meticulously enabled the complex nuclear alchemy that transforms hydrogen into the entire periodic table. We are not just stardust, we are the product of a universe whose quantum laws were precise enough to forge the elements of life itself. The quantum world seems shrouded in a veil of probability, a place where particles can be in two states at once until we look at them. Yet the world we experience is solid and definite. How does this strange quantum fuzziness resolve into the single, objective reality we all agree upon? Quantum Darwinism offers a fascinating answer, proposing that reality becomes objective through a process of natural selection. In this view, the quantum states we ultimately perceive are not chosen by our consciousness. They are the ones that are most robust, the ones that survive a relentless process of environmental interaction. Every object, from a dust mote to a distant galaxy, is constantly interacting with its surroundings through a storm of quantum fluctuations. Photons of light bounce off it, air molecules collide with it, and the faint gravitational field tugs at it. Each of these interactions carries away a tiny piece of information about the object's state. The key is that for most quantum superpositions, these interactions are destructive. A single photon scattering off an electron that is in two places at once would record a confusing, contradictory piece of data. That state is fragile and quickly collapses, but some states are different. They are stable. When a photon scatters off an object in one of these stable states, it reliably copies the same, definite information. This information is then redundantly imprinted onto the environment, broadcast outwards by countless quantum interactions. It is copied over and over again, like a message being printed in billions of newspapers. Our perception of reality is not a direct observation of the object itself. Instead, we are simply tapping into this cloud of redundant information that has been disseminated into the environment. We intercept a few of the countless photons that have all recorded the same stable state. The reason we never see a table in a superposition of being both here and there is that such a state would be instantly obliterated by its contact with the air and light around it. It cannot create stable, redundant copies of itself. Only the states that are resilient, the ones that can be widely and consistently copied, survive to become our shared reality. This process is quantum Darwinism, where the fittest states are selected for survival by their ability to replicate their information. The solid chair you are sitting on feels objective because its quantum state has been broadcast to the universe, and you are just one of many observers who can access that public record. So the next time you look at a familiar object, consider that its very definiteness is a testament to a silent, continuous process of quantum selection. A battle for stability won long before your eyes ever opened. This cosmic destiny for information might be locked within the black hole's deepest secret. The final state proposal offers a radical and elegant solution to the information paradox, one that imposes a single, unbreakable law at the very heart of destruction. It suggests that the singularity, the point of infinite density at a black hole's center, is not a lawless frontier. Instead, the fundamental rules of quantum mechanics demand a specific, unique quantum state for this final boundary. Think of it as a cosmic filter, a one-way mirror with a very particular reflection. Any matter or energy, any information that falls toward the singularity, does not simply vanish. It is forced to align with this mandated final quantum condition. The journey of every particle, every quantum fluctuation crossing the event horizon, is rewritten to conform to this ultimate cosmic rule. This process does not destroy information, it scrambles it. The intricate details of a fallen star, the unique spin of every electron, are not erased. They are chaotically mixed and encoded into the fabric of the singularity itself. This scrambled information then imprints itself upon the Hawking radiation slowly leaking from the black hole. The radiation is not random thermal noise but a complex message, a cryptographic puzzle containing the complete history of everything that ever fell in. The information is preserved, but in a form so thoroughly mixed that it is effectively impossible to decode without knowing the precise key of the final state itself. This idea imposes a strange and unavoidable destiny on the quantum fluctuations we have followed. Even the most random virtual particle pair born at the event horizon has its fate sealed by this boundary law. If one particle falls in, its entire quantum history is instantly processed and filtered through the final state, its information inevitably woven into the outgoing radiation of its escaping partner. Nothing that enters a black hole is ever truly lost. It is simply transformed into a different kind of cosmic story, one written in a language of ultimate entanglement. The black hole becomes a cosmic transformer, not a shredder, turning the specific into the scrambled and ensuring that no quantum whisper, no matter how faint, is ever completely silenced by the darkness. Our cosmic history lacks a definitive starting gun. Stephen Hawking and James Hartle proposed a universe without a beginning, a cosmos that simply is. Their no-boundary proposal elegantly sidesteps the troublesome singularity of the Big Bang by reimagining the very nature of time. In this model, if we could rewind the cosmic clock to the very start, we would not find a point of infinite density. Instead, we would witness a profound transformation. Time itself would smoothly morph into a dimension that behaves like space. Imagine the universe not as a timeline starting at a point, but as a closed, curved surface like the surface of the Earth. The North Pole on this cosmic globe is not a moment of creation in time. It is merely a point where the dimension we experience as time curves into a spatial dimension, forming a perfectly smooth, finite surface with no edge and no boundary. There is no before the Big Bang because there was no time for a before to exist. The universe is a self-contained geometric object with all of history contained within its seamless fabric. This has a stunning implication for the origin of everything, including the quantum fluctuations that seeded our galaxies. In this no-boundary geometry, the universe and its initial conditions would not be set by some external law or prior cause. They would arise from nothing because the geometry itself is the entirety of reality. The primordial quantum jitters that became the cosmic microwave background and the large-scale structure of the cosmos were not imposed on the universe. They are an inherent, necessary part of this self-contained geometric entity, emerging naturally from its smooth, finite shape. The universe did not come from nothing in a burst of energy. It is nothing, a perfect, self-consistent geometric form whose internal quantum tremors gave rise to all the something we see around us. Are we living inside a cosmic story that wrote its own first chapter by having no beginning at all? Our final theory is perhaps the most fundamental of all, a proposal that strips reality down to its barest essence. The mathematical universe hypothesis, championed by physicist Max Tegmark, makes a claim so absolute it borders on the philosophical. It suggests that our physical reality is not merely described by mathematics. It is mathematics. In this ultimate view, the cosmos is not a collection of objects obeying mathematical rules. It is a specific, very complex mathematical structure, and we are self-aware patterns within it. Think of a triangle. It has certain immutable properties, like the sum of its angles always equaling 180 degrees. These properties exist in an abstract Platonic realm, independent of anyone drawing one on a piece of paper. Tegmark proposes that our universe exists in exactly the same way. It is a mathematical object whose properties are what we call physics. In this framework, the quantum fluctuations that have been our constant guide are not jitters in a physical field. They are the inevitable outcomes of the mathematical equations that define the structure. The seething vacuum foam, the primordial seeds for galaxies, the very laws of gravity and quantum mechanics are all simply mathematical relationships playing themselves out. The universe computes itself because it is, at its core, a computation. This leads to a staggering resolution of the mystery of existence. Why is there something rather than nothing? The mathematical universe hypothesis offers a stark answer. Nothingness may be an impossible concept because mathematical structures necessarily exist. They do not reside in a physical location, they just are. The number 7, the properties of a sphere, the equations of quantum field theory all have an abstract reality. Our particular universe is simply one of these structures that has the property of containing self-aware substructures like us, who can perceive its mathematical beauty. This idea transforms our cosmic story into something both profound and humbling. The entire journey from the first quantum tremor to the rise of conscious life was not a physical process in the conventional sense. It was the unfolding of a specific, rigid mathematical truth. We are not biological beings living in a physical world. We are complex mathematical patterns, temporary configurations in an eternal equation, briefly aware of our own existence. Is the ultimate answer to every cosmic question simply a number waiting to be found? We have journeyed from the seething energy of the vacuum to the holographic edges of reality, exploring 30 mind-expanding theories that attempt to decode the universe's quantum jitters. We have seen how these microscopic tremors could have built the cosmic web, guided by a pilot wave or branching into infinite worlds. We have considered the possibility that our entire existence is a simulation running on a cosmic computer, or a timeless mathematical structure simply expressing its own inherent truth. While we may never know for certain which of these visions is correct, this incredible pursuit places us at the very frontier of human knowledge. The study of quantum fluctuations is more than just physics. It is a deep philosophical quest that challenges our understanding of reality, time, and our own place within the cosmos. It pushes the boundaries of what we can comprehend, reminding us that the universe is far stranger and more wonderful than we ever imagined. So we turn the question to you. Which of these theories blew your mind the most? Do you have your own favorite explanation for the universe's quantum jitters? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos.